Okay, hello everyone and welcome. Hope you all had a nice weekend. It is one more week until spring break, as I'm sure you're probably already aware of. I am also looking forward to spring break. I do kind of have to work, but at least I don't have to go to class, so it is a little bit more chill. I do want to bring some things to your attention just to make sure you know what's going on both before and after spring break, since there are some important things coming up. Assignment 5 is due this week in your lab section on Wednesday. I always get students ask me how spring break is going to affect late coupons. I'm happy to tell you that the clock is effectively paused over spring break. So that means you can submit assignment 5 after you get back from spring break using late coupons. That is a possibility. So we will likely be resuming office hours on Monday the 17th. So that would be the first opportunity that you would have to demo that assignment after spring break. If you don't get it done before you leave for spring break, that would be your next opportunity to do so. And you're not going to be deducted additional late coupons for spring break. The clock will be paused. It will resume once we get back from spring break. So want to make sure everybody's aware of that, and I also want to make sure everybody's aware of the fact that once we get back from spring break, we are going to have our second exam. So this is the last new set of material. This material will be on the exam that is coming up after spring break. But it is not a cumulative exam, so it's only going to be over what we've talked about since the prior exam, which is sections 4, 5, and 6. That's going to be the content that'll be on the next exam, exam 2. And as usual, we'll have our exam 2 review session. So the next time I see you after spring break on Monday, we'll be in this room to have an exam 2 review session. I do not have all of the exam materials posted quite yet. I'm hoping to get that posted tomorrow, and I'll be sure to throw up a little announcement on Piazza once I have the exam study materials posted for you. But the format will be exactly the same as last time, so no surprises there, hopefully. Just want to make sure that you're not surprised by the fact that we do have that exam coming up. I think that's all I wanted to chat with you about regarding the schedule. Does anybody have any questions about logistics or spring break or any of the stuff like that before we hop into today's topic? You all good? Awesome. Great. So today's topic is kind of a doozy. I think that this is definitely considered to be one of the trickier topics that we cover in this entire class. And that might not be exactly what you wanted to hear, especially considering that last week's material that we covered about methods is also a bit tricky. It's also one of the more tricky topics that we cover in this class. And I want to make clear right out of the gate that what we're talking about today relating to recursion depends so much on what we talked about last week regarding methods. So if you were not here last week, or you couldn't do the materials last week because you were sick or because something happened, I would like to say right now that you're probably not going to get a lot out of what I'm talking about today. It is absolutely crucial, absolutely essential that you have at least a basic understanding of the materials from Module 5 regarding methods and how methods work. We're going to be reviewing a lot of that material today anyway, because it's such a big part of recursion. But you're not going to stand a chance at learning this stuff if you do not at least have some basic understanding of the stuff we talked about last week. So that's not to try and shame you or anything. I'm just trying to make sure you're prepped. If this isn't the best use of your time, I might suggest go back and study last week's material, right? If you have to. I know people don't like having to go backwards or staying behind, but I promise you, you're not going to be able to pick this stuff up if you do not have a good grasp of that material. So please use your time wisely. And if you're having trouble catching up or understanding last week's material or understanding this week's material, I will still have office hours Tuesday, Thursday, and Friday this week. I'd be happy to chat with you about that. Happy to go over any of these concepts. Happy to reinforce whatever you need help with. But today we're going to be talking about recursion. I'm going to work through actually a couple of examples from the prep work today. I also brought an example of my own that I'm going to work through today, but I'm just working in the exercises 2 repository today. I don't have an extra repository for you or anything. And we're going to start with this very simple factorial example. This code is actually given to you as a recursive method already, so I would like to talk about that. But I also, before I get into that, want to talk about what recursion actually is and what it's used for. So I think one of the hardest parts of this class, I can show you code, right? But knowing when to use a particular piece of code, knowing when to use a particular tool, is one of the trickier things. And so with recursion, that's actually one of the easier things about it. Recursion is used for the same thing that we use loops for. Recursion is just another way to perform repetition. In fact, I'm going to show you a lot of examples today where I give you the example in recursion, and then for this one I'm going to show you how to do it using loops. And the other way as well, I'm going to say here's an example using loops. Let me show you how I would do this using recursion, right? Anytime I am using a loop, I could also solve that problem using recursion if I want to. So it's just another way of doing something that we kind of already know how to do. I would even go so far as to say that if I'm thinking about how to solve a problem and I know I can solve it with a loop, right? I'm fairly certain I could do it with a loop, and I'm trying to make this choice, right? Do I want to use recursion or do I want to use a loop? Me, personally, I'm going to pick the loop 99 times out of 100. I like loops. I think loops are nice, direct, concise. I think for especially simple things, recursion is maybe not the best choice. There are some problem types, however, where recursion is a natural fit, where loops just aren't going to work. So the opposite is not true. If I have a loop, I can turn that into something that uses recursion, but the opposite is not necessarily true, right? If I have something that is recursive, I don't necessarily have that same ability to turn it into something that uses loops. There are certain situations where recursion is going to be the better way to go, clearly. And I'm going to show you one example at the end of class today to try and prove that point. But most of the examples that I show you in class, most of the examples that you work on in the studio and on the upcoming homework assignment, you might say to yourself, I could do this using a loop. Why can't I do this using a loop? And actually, that's true. I'm not going to deny that. You could solve it using a loop, and in most cases probably would solve it using a loop, but I'm trying to get you to learn recursion, so I'm going to ask you to not use loops and use recursion instead. We often will not mix those two things together. I'm either going to use loops or I'm going to use recursion, and not both, at least in this class. Maybe in advanced comp sci, you'll start to blend those a little bit more, but in this class it's usually a one or the other type situation, not both. So with that in mind, let's take a look at this simple recursive method that you were given as part of the prep work and try to break it down, starting with the strict definition of recursion. What does it mean to say that something is recursive? That means, so a method is something that can be recursive, and a method is recursive if that method calls itself. So that's a very short, concise definition of recursion, but it requires a pretty, as I said, it requires some knowledge of what methods are and how they work. Specifically, method calls, meaning that, okay, in this particular example, you can see that I am creating a method called factorial, and I am using that method within it, right? So I am using the factorial method to solve the factorial method. That's recursion. At the end of the day, that is actually all that you need to say that a method is recursive. So all I need to say that a method is recursive is to find a method call somewhere inside of that method body. Now, that alone will not necessarily give you effective recursion or useful recursion. So there are a couple of other things to keep in mind when you're trying to use recursion if you want to make sure that you're using it properly. So that you don't run into some errors or mistakes. I'm going to actually show you some of those errors today so that hopefully if and when you run into them, you won't be totally surprised. You can actually see that this recursive method is broken into two parts, and that's not unusual. Almost all recursive methods are going to be broken into two parts. This first part up here at the top, this is actually the non-recursive part. This is what I would call the base case. The base case is, when do we stop? So just like loops are going to repeat until they hit some sort of condition, right? That's how we tell loops to stop. We also need to have a way to tell the recursive repetition that it needs to stop. And that's what we call the base case. So this base case is usually going to be some known value, right? This isn't something we have to compute or something we have to determine. This is just something that we know. You can see that for this case, we're saying that the factorial of 0 is known to be 1. We know that. That's just kind of defined that way, right? Factorial of 0 is known to be 1. And then for the other computations of factorial, we jump down to this else statement. This is what I would call the recursive step. So this is where the recursion's happening. You can see that very clearly. There's that factorial method being used. But you have to be careful about how this recursion happens. Not only does it need to, of course, solve whatever problem we're trying to solve, right? So factorial is done in a particular way. If you need a little refresher on factorial, you would say 4 factorial is equal to 4 times 3 times 2 times 1, which is equal to 624, right? Is that correct? 4 times 3 times 2 times 1. Yeah, I think that's correct. Does this give me 24 when I run it? Let's see. Yes, it does. Awesome. Wonderful. I actually have the factorial of 4 given down here in the main method to test this out, and it is correctly computing the value of 24. But how do we come up with this? How do we come up with this statement? That's, one of the trickier parts of working with recursion. People will understand how to walk through the code, kind of, but how do we actually generate this in the first place? The idea here is that we want to define the problem in terms of itself. So I want to take this problem that we're trying to solve called factorial and define it in terms of itself. Or another way of thinking about that is, here I've written out what 4 factorial equals. Do you see another instance of factorial in this description that I've written out? I hope that you do. I hope that you see that if I wanted to, I could actually highlight this section and call that 3 factorial, right? I can call that 3 factorial. So if I wanted to write this, I could write this as 4 times 3 factorial. And that's effectively what this statement is saying here in a more general way, right? It's saying that for the factorial of n, so n factorial is equal to n times n minus 1 factorial. Does everybody see how I got from the original to that next step? So once you have this problem defined in terms of itself, that's recursion. That's when you know that, okay, this is my recursive step. The other thing to consider, remember that base case is when we stop. That is our known stopping point. Just like when we use a while loop, we have to ensure that the condition will eventually be false. When we're using recursion, we have to ensure that we're eventually going to hit that base case. So how do we guarantee that we're eventually going to hit that base case and stop? If we don't hit that base case, then we run the risk of, just like we saw with the while loop, it can go infinitely, we would run into the risk of recursion that is going infinitely and never stops. So I don't want to simply restate the problem directly. It needs to be restated in such a way that it is, you might hear it referred to as a smaller version of the original problem, or a simpler version of the original problem, or one step closer to the base case than where I was before. Because I'm starting at n, some positive value n, and I'm always going down by 1, I know for a fact that I will eventually get to n is equal to 0. I will eventually hit that base case. That is guaranteed to happen. Okay? And so then actually, there's a couple things that I want to do with this example. One, for basically every example I show you today. I want to contrast that with what I would call the iterative solution, which is the one that uses loops. And for that case, I would say that if you're trying to mimic recursion using loops, a while loop is usually going to be the loop style that kind of fits with recursion the best. So I'm going to try and use a while loop to do this. I'm going to try and write a method that behaves exactly the same way as this, but just uses a loop to do it instead of recursion. That way we can kind of compare and contrast the two approaches. So let's go ahead and create our method. It's going to have the same return type. I'll call it factorial loops. So I know this is the one that uses loops, and the other one is the one that doesn't use loops and uses recursion. So the stopping point is going to have to be roughly the same, right? I'm going to stop at 0. Or we could think about it perhaps working in the opposite direction, starting at 0 and counting our way up to n with the loop. I'm going to try and mimic this as close as I possibly can, though, and I'll say while n is not equal to 0, we need to do some multiplication here, right? I need to multiply n by some value. I actually need a variable to store that value. So my result is going to start at probably 1. Be careful not to use 0 here. Factorial uses multiplication. So if we start this variable at 0, that's going to not work out too well for us. We have to be careful to start it at 1. All right, if I haven't hit 0 yet, then I will just multiply my current result times n. And then I'll make sure to subtract 1 from n, right? So if n starts at 4, I'll multiply by 4, then go down to 3, then go down to 2, then go down to 1, then go down to 0. And eventually, I will stop this loop and return my result. I don't want you to just take my word for this, though. Let's come down here and see if we can switch up this method call to use the loop version, and hopefully we still get 24 back out. Good. Yeah, we do. We do. So you can kind of actually see, right, where these pieces match up. The condition here is not exactly the same as the base case. It's actually the opposite of the base case, which makes sense. The base case says, if this is true, then stop. And then we're kind of saying the opposite here. We're saying if this is true, keep going. So the fact that they're the opposite of one another kind of makes sense. And then the stuff that happens inside of the while loop is the repetitive part. So that's going to correspond with the recursive part of my recursive approach, where you can see the multiplication as well as subtracting 1 from n, both making an appearance, right? All of the same pieces are there. It's just the way that we get there is a little bit different. This example uses a loop to perform the repetition, whereas recursion uses repetitive method calls to perform the repetition. And I'm going to step through this in the debugger next. I just want to pause and see if anybody has any questions for me before I do that, because I want to take a look at this in a lot more detail. So what I'm going to do is set a breakpoint right here on line number 10. And I want to run this through the debugger and make sure I understand exactly how this recursive operation is working. I think most people, by this point are familiar enough with loops that I'm not too worried about having to explain this in step-by-step detail. But methods are still pretty new to us, and recursion is very new to us. So let's set a breakpoint on line 10. I set it right at the base case. I'm going to hit the debug, which will hopefully switch me over. No? What happened? It's not doing what I want it to do. Let me try right-click debug as. Something's not working properly. What am I missing? I'm a little bit confused, to be honest with you. Stop that. That was from earlier today. I don't think that was getting in the way, was it? Yeah, it's not stopping at my breakpoint. Why aren't you stopping at my breakpoint? Let me try and put it here on line 30 instead, since it's not... I'm a little bit confused by that, but let me see if it likes this. I'm sorry? Oh, I didn't change... Thank you. I didn't change it back to the recursive one. Thank you. That's why I never hit my breakpoint. Got to change that back to the recursive one. It was never calling this method, so it was never hitting the breakpoint. That's totally my bad. Awesome. This will work anyway. We can break on line 30. Might be a better place to put it anyhow. Okay, just a quick little review / refresher of what we talked about in class last week regarding methods. The main method is where we begin, right? The main method is the entry point. So this is the very first line that we're running as part of the program, and it says that we're going to compute the factorial of 4. Notice over here on the left, we again have, what is this called over here on the left? It's a stack. Yeah, that's an exam question. That's definitely a question you might see on your exam after spring break. This is the method call stack. So every time we call a method, I'm going to see that method call on this stack. The only method that I see right now is main. I haven't called anything yet. I'm still in main. I haven't done any recursion yet. Still just getting started. In order to actually see the execution of the factorial method, I'm not going to click step over. Step over does not go into the method calls. Step into is the one that we want to actually view the method calls. So when I click step into, notice what happens. My stack has grown. I see that main is here on the bottom. It's always going to be on the bottom since main is where we start. And now I can see that I have factorial just above that. So I have called the factorial method. Over here on the right-hand side, I can see that I've called it with the value of n being 4. So it's going to check my base case first, which is typically how we want to do it. I'm always going to ask the question, should I stop? Right? Or should I keep going? So we're going to ask, is it time to stop? And the answer in this case is no, it's not time to stop. So we're going to come down here and we're going to do this recursive step, but this is another method call. Right? This is a method call. And when I call methods, that takes me back to the beginning of the method and adds another method call on the stack. So when I click step into on this line, notice that now I see main and then 2 versions of factorial. Think about what that means for a second. We were just in factorial. We made another copy of factorial, but that first one is not over yet, right? That first one cannot figure out what its answer is supposed to be until this one figures out what its answer is supposed to be. So that very first one is just sitting there waiting, just sitting there chilling, waiting until this figures out what it's supposed to do, in which case, then it can do its thing. So here we are. We can see n is equal to 3. We're going to do the same check. Have I hit the base case? No, I have not. So I need to do more recursion, and surprise, surprise, when I step into that, I see, okay, again, another one. We're up to 3 now. N is equal to 2. That still doesn't tell us to stop, so there's another recursive call. N is equal to 1. That still does not satisfy our base case, so here's another recursive call. And now finally we can see that n is equal to 0, but all of these other method calls are still waiting. They have not finished yet. I think it's very, 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 very important to understand. They are still waiting in the background. I eventually need to go back to all of these and resolve these method calls with the proper answer. But first, we're going to hit our base case. This is the case where we're not going to do recursion. N is 0. I know what the answer is when n is 0. The answer is 1. 0 factorial is 1 by definition. So, okay, I return the 1. Recall from our conversation last week that returning does 2 different things. It stops the method. The method is over once you hit a return statement. And it also says that this is the result. It has to match the return type. But this is the answer. 0 factorial is 1. So it's going to take that 1 and it's going to pass it back up the stack. So that 1 is going to be passed up to this version of factorial when I click the step button. Notice that my stack's now starting to shrink. I hit my base case. That version of the method that was called for the base case is done. It did its job. It returned a 1. So now I can compute this. I can say that, okay, this gave me 1. 1 times n, which is in this case is 1, is still 1. So it's going to compute that and return that up to the method call that was just before it. So, okay, here we go. Stack shrinks again. I got my value of 1 returned. N is 2, so now I get a value of 2. Step again, my stack shrinks by one more method call. I got 2 from the prior one, from my prior recursive call. N is now 3. 3 times 2 is going to get me 6. All right, so I take that 6 and return it. This is my original factorial call. This is where I all started. This is where the factorial recursion started with n is equal to 4. The prior version of factorial gave me a 6. 6 times 4 is going to give me 24, and that is my answer, which will then get printed out. Every instance of recursion is going to work in a similar way. Call the method, call the method, call the method, call the method a bunch of times until you eventually hit that base case, and then we have to go back, right? I'm not done when I hit the base case. I have to go back and revisit each of those methods again and compute the answer on my way back up to the original method call. Are there any questions about that process at all that I hope that was helpful to see it step by step, and it's very useful to understand. One other thing I want to do, actually a couple other things I want to do with this example before we move on to another one. We can actually figure all of that out ahead of time. We don't need to step it through the debugger or compute the math ourselves. In fact, this is another great thing to, circle it or put a star by it in your notes. We can use something called the substitution method. This will almost certainly be on the exam that's coming up in a couple of weeks. Here's how the substitution method works. Let's say I want to figure out what 4 factorial is as it goes through this code, right? The way that I would figure that out is I would say that the factorial of 4 is equal to, now 4 doesn't satisfy my base case, so factorial of 4 is equal to 4 times the factorial of 3, right? So I'd say 4 times the factorial of 3. Well, now I have to say, oh, I don't know what this is. Let me figure out what this is. So on the next line, I'll say the factorial of 3 is equal to, still not going to hit the base case, so that'll be equal to 3 times the factorial of 2. Okay, now I have to figure out what the factorial of 2 is. Factorial of 2 is equal to 2 times the factorial of 1. All right, now I have to figure out what the factorial of 1 is. Factorial of 1 is equal to 1 times the factorial of 0. Okay, now we're at our base case. So now I can simply say that the factorial of 0 is equal to 1. That's exactly what's defined by our base case here in the recursion. But we're not done yet. It's called the substitution method. We haven't actually done any substitutions yet, but we're about to. The substitution then says, take this 1 and substitute it into this statement for the factorial of 0. So now I can say, okay, the factorial of 1 is equal to 1 times 1, which is equal to 1. And now that I know what the factorial of 1 is, I can take the value for factorial of 1 and substitute it back into this expression, right? So I'm going to say, okay, the factorial of 2 is equal to 2 times 1, which is equal to 2. And we're going to do that same thing all the way back up, just like we saw in the debugger. It's exactly the same process like we saw in the debugger just now. So, okay, the factorial of 3 is equal to 3 times 2, which is equal to 6. And then the factorial of 4 is equal to 4 times 6, which is equal to 24. Again, notice I figured all of this out on paper and pencil just by tracing through the code. And it's exactly the same way that the debugger is going to figure it out. It's exactly the same way that the computer is going to compute this. So again, almost pretty much a guarantee, 99% chance that I'm going to ask you to do a substitution method, give you some recursive method on the exam, and say, write out the substitution method for this method call. And then this is what I want to see. I want to see the steps all the way down to the base case, and then I want to see the computations all the way back up to the original method call. Any questions I can address? Let's take a look at what happens in some bad situations, right? So let's take a look at some errors that you might run into. I mentioned infinite recursion before. That is technically a thing. Infinite recursion is a thing. However, normally you won't see it. So if I made a mistake, like this, if I change this to a plus, that one little change from a minus to a plus creates a problem for me. Because now if n starts at 4, it's going to keep going up by 1, and it's never, ever, ever going to hit 0, right? It's just going to keep getting bigger and bigger and bigger. I'm never going to hit my base case. So what's going to happen? What's going to happen if I try? Well, let's give it a go. Hit the go button, and oh, there's an error. Oops, I didn't mean to click that. My fault. Go away. Here's an error. Actually, not just one error, but a whole lot of them. There's a bunch that's being displayed here. If we go all the way up to the top, though, you get to one of the most famous computer coding errors that you'll ever run into, called a stack overflow error. This is one that deals specifically with, we're talking about the exact same stack we were talking about just a moment ago, the method call stack. What happened here is that it called this method this many times. However many lines you see here is how many times it tried to call that method. And eventually it's like, we still haven't hit the base case on this, and the stack's getting really big, and I'm worried that we're never going to hit the base case. You've overflowed the stack. You've basically said, you've called too many methods. I'm not going to deal with this, right? There's too many methods being called here. I can't handle it. I mean, it's a good thing the computer stopped us, because again, if it didn't, we would hit infinity eventually, right? It would just go forever. Just try and do this forever. We don't want that. That's a bad thing. This stack overflow is usually capped by default at like 200 or so. So that means that it tried to run this recursion a couple hundred times before it was like, I don't think you're going to get there. I don't think you're going to hit that base case. I think this is bad. Most recursive algorithms don't need that many steps to hit the base case, right? It's not necessary. So, if you find yourself in that position, you probably are in an infinite recursion situation. In most cases, you need to either check your recursive step to make sure that it's getting closer to the base case, or check your base case. Maybe your base case isn't specified properly, so it's not stopping at the proper time. But I did want to show you an example of what will happen in that case. Okay, I believe that's all I had for the factorial example. I'm going to switch over and do another one next. We're going to go the opposite way this time. I'm giving you a method. This isn't in the prep work, by the way. I brought this one with me today. This is one that I brought along as a bonus example. It's a method that is supposed to count how many odd values exist within an array. So I give it this test array that has 1, 2, 3, 4 odd values in it, right? So if I pass this array into my method, I want to see that it found 4 odd values. Use the modulus to do that. I'm not too interested in this, but it is a good old for loop, right? It's a good old for loop that creates a variable for the count and then iterates through and returns the count when it's done. And it works. It definitely works. Found 4 values. But I want to do this recursively. I want to redo the same thing using recursion. So let's try and think about, I'm not going to do the full substitution method first, but I do want to kind of try and think about how to find the recursive substructure. So defining that problem in terms of itself. The way that this code does it, think about how this loop does it. It checks to see if the first number is odd. If it is, then it bumps the counter up by 1. But even if, regardless of what happens, right, whether this value is odd or not, once we've made that determination, we move on to the next value and we look at that. We move on to the next value and we look at that. We move on, we move on, we move on until eventually there are no more values to check. I would argue that recursion could use a similar approach where the base case is, are there any more values to check or not, right? Have I hit the end of the array or not? So that's based on my position within the array. I have to know which of these values I'm currently looking at, what's my current index, and then compare that against the length of the array. But what about the recursive substructure? So let's say I want to do a simple example of like count odd of 1, 2, 3. This is meant to be more handwriting than code, right? So the way that I think about this is that, well, okay, I look at the very first value in the array, I check whether it's odd or not. It is odd, so I'll say that there's at least one odd value. I know there's one odd value, right, the one that I just looked at, plus however many odd values there are in the rest of the array. So everything afterwards. So it's going to be 1 plus count odd of 2, 3. Although in practice, this looks like I'm making like a shorter array, right? Or deleting them. In practice, we don't do it that way. In practice, we would say I++, right? Move our index variable over 1. So it might actually look something more like this, where I start at 0, and my recursive call is actually 1, right? The next time through, I don't want to look at this number. I want to look at the value in position 1 instead. It's probably a more accurate representation of what this recursion would look like. And with this in mind, we can already kind of start to try and write our recursive implementation. Let's give it a go. Count odd. I'm going to put an R on the end to indicate that this is the recursive version of the method and not the iterative version like the one up above. It'll take in our array of values just like before. And so you can see in this example, the first thing I do is I make a variable for my counter. That makes sense to me. So I'd say int count is equal to 0. Wait a second. I think we might already kind of have a problem here, right? Think about if this is recursive. Recursive means repetition, which means that every time I call this method, it's going to set count to be 0. Do you see the problem? See the problem I've run into? I don't want to reset count to be 0 every time. I want to set count to be 0 once and then let it get updated. And then if we go on and we try to write the base case that we just identified, right? It's based on my position in the array as well as, how big the array is. So, okay, I could say like if values dot length is greater than or is less than, well, I want to say like I here, right? But what is I? I don't have I, right? There's no for loop. I haven't said for. So hold on a second. Where does this piece of information come from? How do I get access to it? Think that in this case, right, we're using the loop to perform repetition. That means that one trip through this loop should be roughly equivalent to one trip through this method, meaning that this value of I is going to be different every time this method is called. At least I want it to be. So I can't just say, int I equals 0 here. It's the same problem as before with the count. Right? It's the exact same problem as before. I want I to start at 0, but I only need to say that once. I don't need to say that a whole bunch of times. So in order to get around these issues, we're going to actually create an additional method. This is a popular technique that is used with recursion. It's called a helper method. So we're going to use 2 methods to pull this off, not just one. One of the methods is going to do anything that's not repetitive. So if there's anything that has to happen once, I'll do it in the the non-recursive method, the one that's not going to repeat a whole bunch of times. And that allows me to keep the repetitive stuff in the recursive method. So let me show you how that would work in this case. This is the method that I originally started with that takes in the array of integers. So this is where all the non-repetitive stuff is going to go. So I'll set up my count variable, and I'll set up my value for I. That's totally fine. I can set these up. But then what I want to do is I want to pass those values. I want to pass execution off to my recursive method, to the method that's going to be doing the repetition. So that method doesn't exist yet, but I almost always would name it something like count odd helper. It is a helper method. I'll plug in the array because I need to have the array, but I'm also going to plug in the counter, and I'm also going to plug in I. Right? So I have more parameters here than I did here, but I can do that. There is no rule saying that I can't create my own methods. In fact, I want you all to have that confidence to create your own methods as programmers. Methods make our lives easier. I know they're a little scary and intimidating when you're first learning about them, but they, in general, are a good thing. And we want to include lots of methods. Lots of methods is a good thing. So we want to include additional methods, especially if we have a good reason, and this is a great reason. We're using this helper method to do really a couple of things for us. It isolates the repetitive stuff from the non-repetitive stuff. That's one big thing that a helper method does for us. But a helper method also allows us to add additional parameters that we can use to track important pieces of information during the recursive part. Much like this for loop is keeping track of I and manipulating the counter, right? We need to include those as part of our helper method so that the recursion can access those values as well. So helper methods really used for a couple of different reasons, and I'm going to go ahead and create that now. Helper method isolates repetitive stuff. Also allows us to add additional parameters to ease computation. So our helper method is going to take in 3 parameters, right? The first one is this integer array called values. The second one is our counter, which we can just say, count. And the third one is, I, which represents our current position in the array. Once we have those 3 parameters, we can now actually return to thinking about how to implement our recursive substructure here. Our base case has to do with when the index has gone off the edge, right? When the index has gone off the edge of the array. So I'll say something like, if the index is greater than or equal to values.length. This is my base case. No more values to check, right? What's the answer here? How many odd values have I seen if I have gone off the edge of the array? A little tricky, actually. I think there's more than one way you could do it. I think there's an argument to be made for returning 0 here, but I don't think that's actually correct in this particular example. I think returning the count might be better. We could even just leave this a little blank for now until we come down here and take a look at the recursive step. Using this diagram that we saw before, we can see that, okay, we have to check, right? We have to check and see whether it's even or odd. So first, let's do that if statement. If values at index mod 2 is not equal to 0, or is equal to 1, however you want to say it, then count plus plus. And regardless of whether this is true or not, we need to do the recursive step, which says move on to the next value. Check the next value, please. So, okay. Count odd helper needs 3 parameters. It needs the values. It needs the counter, which may or may not have just gone up by 1, right? Maybe it did, maybe it didn't. And then we need to plug in the index, but we need to actually say move over. So that index plus 1 is very, very important, right? Okay. So with that in mind, let's try and wrap up a couple of loose ends here and see if we can't test this out. Up here, we need to return the counter. So when it finds the first odd value, it bumps the counter up by 1, right? And then we pass that counter along. So that counter is always going to be up to date. Always. There's another way to do this, actually. I might show you that alternative implementation in a bit. But the way that I've decided to do this in this particular case, our base case is going to be to return our counter. That means we're finished counting here, right? When we get to the end, we're finished counting. Just say what the answer is. Say the result of the values you've counted. Otherwise, check the next value to see if it's odd or even, bump up the counter. And then we also need to be careful. There's an error right here. It says we have to return a result of type int. I have to say return this, right? To make sure that the answer, whatever answer gets computed, is passed along. It's passed along out. Up here, it's actually a similar mistake, one that I made somewhat intentionally before. I have to generate an int, so I also am missing a return here as well. And we're now ready to test this out, and I want to run this one through the debugger as well. I think it's a bit more complicated than the previous example, but still recursive. Uses the helper method. I'm going to go ahead and set my breakpoint right here on line 20. No, I take that back. I'm going to turn that off, and I'm going to come up to the main method and put it right here on line 7. And I'm going to change this to be not the one that uses a loop, but I'm going to put the R on the end so that I'm using the recursive version of this method. And let's start up the debugger. Start walking through this one, starting from the breakpoint. Here I am on line number 7. You can see that I'm still in the main method, so that's the only thing that's on my stack. I've got this test array that I'm about to start checking for odd values, and when I step into it, I actually do not step into my recursive method. I think that's another important thing to understand. If you're using a helper method, we don't call the recursive method directly. The helper method is the recursive one, but it is called via the non-helper method. So I always call the non-repetitive method first and let that method pass execution off to the recursive method. Yes?
Why do we need 2 methods to run count? Can't we just use count out helper to do all the tasks?
Okay, so if I pretend that this method doesn't exist, right? Think about what I would have to do. I would have to initialize my counter somewhere. So I'd probably put it here. But think about what this does. This is going to erase my counter every time. This method is going to be called a whole bunch of times because it's recursive, it's repetitive. And every single time I'm going to say, forget about whatever the count used to be, it's now 0. And that's just wrong. That's just not correct. That's because this doesn't need to be repeated, right? This initialization does not need to be repeated. It only needs to happen once. We're using 2 methods to keep the repetitive, recursive stuff separate from the non-repetitive, non-recursive stuff. That's why we have 2 different methods. Yeah. Great question. Any other question I can address? Yes? I'm sorry, say that one more time? If I want to traverse an array using recursion, I'm probably always going to do it similar to this with the helper method, yes. But if I just want to traverse an array in general, I'm not going to use recursion. I'm going to use a loop and do it that way because it's much simpler and much more straightforward, right? Again, this is an example of showing how recursion works, not necessarily the best way of using recursion, just a way of using it, yeah. All right, so if we go back and think about how we're going to step through this, here I am in the non-recursive, non-helper method. I'm setting up my initial values, right? Count is set to 0, I is set to 0, and now that I've done the non-repetitive stuff and set up the variables that I need to help me perform this operation, I'm going to pass execution off to the recursive method, the helper method. So when I step into the helper method, we can see, yes, I'm going to check the base case at first, but I haven't checked anything yet. So my index is still 0. I still have, the entire array left to check. So I'm going to click step over. And here we go. I'm going to check the value at the first position to see if it's odd. It is odd. So it bumps my count up by 1. And now take a look at the next recursive call we're going to make. It's going to send us to the same thing with the same array, but count is now 1 instead of 0. And I, once I call this next method, is going to bump up to 1. So you can take a look. Here I am on the in the method call stack. This is my non-helper method right here. My helper's been called twice so far. So this is the one that's going to be doing the repetition, doing the recursion. Still haven't hit the end yet. Is this number odd? It is. So I'll bump count up again, and let's keep moving along. There's another call, right? I'm going to keep stepping through now until I hit the base case. That one wasn't odd. It skipped over that if statement. That's fine. Index is 3. How big is this array? This array is, okay, so it needs to be, yeah, once index gets to 6. Okay, cool. So I can step through the rest of this now. There's another odd value. Index is 4. Not an odd value. Index is 5. That one happens to be odd. And now here we are at index is 6. Index is 6. That's going to trigger my base case. There's no more values left to check. I checked values from 0 through 5. Notice that my count is 4. That's actually the correct answer. 4 is the answer. I figured out, this one's a little bit different than the last problem. The last problem I went down to the base case and then did the computations on the way back up. This one I kind of did the opposite. This one I did the computations on the way back down, and then when I hit the base case, what happens? I just pass the answer back up, the whole answer back up. So here's my oh, I made a mistake. Oh no, it shouldn't be. No, it should be greater than. What happened? Am I off by 1? Let me see. Okay, I guess my array was 7. Oh, it was 7. Duh. I was off by 1. Sorry. Now we've hit our base case. I was one step too early. Sorry about that. But there's no more work to be done. This is the correct answer. So when I start stepping, you're going to see that, okay, here I am. The stack shrunk, right? Returned 4. But there's nothing left for me to do other than return the answer, which is still 4. So I returned 4. And then this time, I don't know if you saw it. It went really fast. I clicked step over once. The debugger saw that nothing was happening here besides returning. So it collapsed all of them just in one big shot. There was no computations to do. It did, in fact, go through all of those methods. I promise you it did. But it just kind of did it all in one go. And now here I am finally back at the last of the recursive ones. And we're back in the non-helper method where I can see that the answer should be 4, although where did the 4 go? Oh, there it is. Yeah, it's still there. And then that's what ultimately is going to get printed out. So with the helper method involved, it does have this extra step in the middle of setting up any non-repetitive stuff. You don't have to use a helper method in every situation. Though I will say that if you're using recursion with arrays in particular, probably going to want a helper method. That is pretty safe bet. In other situations, not necessary. you just kind of have to think about it. Question?
Yeah, could you repeat like the code like in the main method? I'm a bit confused like
In the main
what it's
method?
doing. Yeah, like directly inside.
Okay, so this is just setting up an array for us to test.
Yeah.
And then this is calling our non-helper method.
Okay.
And then printing out the result that we get back.
Why do we need like the other two? Like besides just like what? Can't we just define the array and then like I'm a bit confused why we need the rest of it.
Why we
Like,
need
the
this?
int result equals. Oh, never mind.
You good? I'm
Yeah.
happy to explain if you need me to. I
misread it.
Okay, that's fine. It happens. I've been there. No worries, no worries. Anybody have another question? I know this stuff's tricky, so I'm very happy to answer questions. If you're feeling confused, I promise you that is totally expected. I was in that exact same position before, I promise you. It's been a little while since I learned this stuff. That's why I feel so comfortable with it now. But when I first learned this stuff, I don't even want to tell you how long ago it was. It definitely blew my mind a little bit as well. So don't feel any shame if you're still feeling a little bit confused about this stuff. I think it's very normal, very natural. Yeah, just be sure to ask for help. Since I'm not... Oh, yeah, in the back.
Yeah, how come for like the helper, instead of putting values count I, do values count index?
Yeah, so that just has to do with the fact that I named my parameter index. This is I get to pick this name. I can call it whatever I want. I can call it I if I want to, but I don't have to. I can call it Doug if I want to, right? Like it's up to me. Call it whatever I want.
For why like you initially define the array as the test, but then for the like parameters you put in values instead of test.
Yeah, so again, this is a very separate variable from this. Methods cannot see variables that are created in other methods. That's because of scope. So this method has no idea that this variable even exists. What we call that is irrelevant. There are two integer arrays that we're talking about. This one is created inside of the main method, and this one is a parameter. And then when we do something like this, we're actually implicitly doing a variable assignment, saying that this parameter is set to be equal to whatever is inside of the parentheses, right? Does that help kind of clarify? The names do not have to match, often will not match, and that's totally okay. Totally okay. Any other questions I can help with before we move on to our next and probably final example for the day? All right, so yeah.
Can we make the count all method and put void? So like
Which one?
count all.
I mean, I can make it void, but I would argue that makes it a lot less useful because I'm saying, tell me how many odd values you find in this array. And if the return type is void, it can't tell me anything. It can't give me any values, right? It can figure that out within the method, but then I'll never get that answer back for myself. Okay, so the examples I've shown you so far, the factorial example and the count odd example, I'm going to be 100% honest with you. If somebody asked me to sit down and do those, like just from scratch, I would not use recursion for those. I promise. I've said this already, but I'm going to say it again because I think it's important. I would use iteration for those things. I think if there is a very clear and easy path to use loops, great. I am going to force you to use recursion because I'm trying to help you learn recursion. So I am going to ask you to do recursion on some problems where using loops would probably be more straightforward. That is a fact. I am going to ask you to do that. But in practice, in the real world, if I can use a loop, I'm going to use a loop. There are people who are the opposite. I know some who love recursion and are like, oh, I can use recursion on this, then I'm going to use recursion on this. And if you're one of those people, then okay, I'm not going to complain about that. But I think most of us would probably rather use a loop, and I don't think there's any shame in doing that. All that being said, there are some problems that are just naturally going to lend themselves better to recursion. And I want to show you one of those to end the day today. The kind of problems that I'm going to show you fall into a category of problems that are called divide and conquer. So the idea here is that we're using recursion. So I start with a problem, and I use recursion to solve, a smaller version of that problem. Divide and conquer says that there's actually multiple smaller versions of that problem. There's not just one smaller version of that problem that I'm going to use recursion to solve, but multiple smaller versions of that problem that need to be solved. The example that I'm going to show you that is a divide and conquer, an example of divide and conquer with recursion is to draw some graph paper. So we're doing a drawing exercise using standard draw, which is a little bit interesting. Let's take a look at the base case. Anytime I'm doing recursion and drawing, which is something that could happen on the exam, absolutely something I've asked before. Definitely plenty of example problems with recursion and standard draw that you'll find in the practice problems that you can use to help prepare. But anytime you find yourself faced with one of those problems, the base case is almost always going to be based on the size of the thing that you're drawing. Once the size of the thing that I'm drawing gets so small, I can't even see it anymore, so I might as well stop. That is almost always going to be the base case when what I'm dealing with is drawing stuff on the screen. There are exceptions, but in this case, I'm drawing graph paper, and so the size is literally how big do I want the boxes of my graph paper to be, right? So my base case is effectively saying that, hey, once you've drawn boxes on the screen that are of that size or smaller, then you need to stop. I don't want you to keep going after that. I don't want you to make even smaller boxes. I want you to stop. You've hit the size that I want. Okay, now let's move on to the rest of it. The next set of instructions here says that as part of this recursive implementation, we're going to draw one horizontal line and one vertical line to dissect the screen. So let me run this. It's not going to do anything yet. Here's my blank screen. Here's the idea. I want to draw one vertical line that splits it in half. I'm going to draw one horizontal line that splits it in half. Okay, so in order to do that, we are going to use standard draw dot line, which requires 4 values, x and y coordinates for both points, both ending points of the line. Okay? So we're going to use the information that we have to try and help us solve this. We are given the lower left x coordinate and the lower left y coordinate of the entire screen. So when I first start out, this is going to be 0 and this is going to be 0 because it's telling us that our square, right, starts at 0, 0. That is the bottom left corner of our square. All right, so I need to figure out how to use that information to draw a horizontal line going across this way and a vertical line going across this way. The size, as we can see starting out, is 1. So the size is this entire thing. So if I want to think about this in relative terms, I don't want to use 0.5, right? I want to do it based on the variables, based on the parameters I have. Let's start with the vertical line. The x position of the vertical line should be size over 2. Do you see that? But it's actually a little bit more complicated than that. It's size over 2 added on to the lower left x coordinate. So lower left x coordinate plus size over 2. Let's try that. It's going to be lower left x plus size divided by 2. I'm drawing a vertical line, so I want the I want the line to start at the bottom, which is going to be my lower left y. And because it's vertical, the x coordinate for the other endpoint is going to be the same. Lower left x plus size over 2. The y coordinate, however, is going to be our existing y coordinate plus the size. So if I want to get to the top, right, I take my lower left y coordinate and I add the size to it. So let's say lower left y plus size. I'm going to run this real quick and then pause and make sure that everybody is with me. There we go. There's my red line running vertically. I think it's very important to understand that I did this based on the values that I have, right? And I didn't hard code in, like 0.5 anywhere. That's not going to do me any good. I want to try and make this work for any square that I could possibly want to draw a graph on. And for the horizontal line, it's actually going to be a similar story. So I'll copy paste this. The x position for my horizontal line is going to start at just whatever the lower left x coordinate is for the entire square. The y position is the one that needs to be bumped up by size over 2, since we're drawing a horizontal line. The final x position is going to go up by size, and the y coordinate is not going to change because it is a horizontal line. So now with this in mind, I've got my cross. You might be thinking, why did you go to such extreme lengths just to draw a cross in the middle of this square? But think about what this problem now becomes. I want to draw smaller, finer grids, and I have 4 quadrants here. So this is where my divide and conquer comes in. I drew a cross in this square, and now I'm going to say, go on to this square right here and do the same thing. Draw a cross in it, which will split that into 4 quadrants, right? And then go to each of those 4 quadrants and do the same thing, draw a cross in those. And go to each of those 4 quadrants and do the same thing and draw a cross in those. And then I'll come to the upper left quadrant and do the same thing. So that's my divide and conquer. I've solved this version of the problem. I now have 4 other different versions of the problem to go and solve. Divide and conquer problems are always going to have multiple recursive calls, one for each of the divisions that I'm trying to conquer. So I would actually expect to see 4 recursive calls here. One for the lower left, one for the upper left, one for the upper right, and one for the lower right. So we need to write 4 recursive calls, and we need to do it based on the information that we have. So let's start trying to piece together the recursive calls, starting with the lower left. I think that's the easiest one to start with. Call the name of the method, that's graph paper. What is the lower left x coordinate of this quadrant? Well, that's very easy. It's the same as the lower left x coordinate of the whole thing, right? It's the same. Hasn't changed. And the same is true for the lower left y coordinate. Also hasn't changed. If I'm starting with the big square, I know the lower left coordinate and the lower y coordinate for the big square. I know the lower left coordinate and the lower y coordinate for this quadrant. It's the same. They are the same. The size, however, is going to go down. Specifically, I would say that size is getting cut in half. This square is going to be 0.5 across, not 1 across like our original. So, okay, let's say size divided by 2. This is one of our 4 recursive calls. So we're not done yet, but we can actually still test it out and see what happens. There we go. It's kind of working in the lower left direction. But it didn't go here, it didn't go here, it didn't go here. And actually, even within the lower left quadrant, it didn't cover, it just kept going down to the left, right? Well, let's start to piece together the upper ones. Let's do the, here, I'm going to mark these so I don't forget which is which. Lower left. Now let's do the upper left, okay? If I start with the big square, I know my lower left coordinates for the big square. The lower left coordinate, the lower left x coordinate for this upper square is the same, right? That doesn't change. So that one's the same, but the y does move up. The y moves up by a factor of size over 2. So for my upper left, I'll say lower left y plus size over 2. And then, just like in the previous example, the size of the overall square is also going to be split in half. I think this will take care of the upper left. Well, let's run it and see. Let's make sure. All right, there we go, lower left. And once it's done doing the lower left, it comes back and does the upper left. Do you see that? And now it's going to hit this one too. So that's pretty cool. You can see that I'm roughly halfway there. If I write the call for the upper right and the lower right, then it's going to come back and fill in all of these upper rights and lower rights that exist in the prior quadrants as well. That's a little mind-blowing, isn't it? Kind of hurts my brain, and I know how this stuff works. It's kind of magical. Yeah. It's the opposite. It does that when size is greater than 0.05, because notice that the base case says to return, which means stop. Return means stop. Size is the size of the square, yes. When I'm done, one of the things on my to-do list is to play around with that number and see how it affects things. So let me finish up these last two calls, and then we can play around with the base case a little bit, because I think that is an interesting thing to think about as well. All right, we're doing the upper right. So, here's where I start. How do I get here? That's moving both of them by a factor of size over 2, correct? Both the x and the y coordinate are being shifted by size over 2. So and then for the final recursive call, whoops, let me label this, which is the lower right corner, our y coordinate isn't going to change because I'm on the bottom, but our x coordinate is. So it would look something like this. And now that we've got the whole shebang, hopefully we'll get all of the sections filled in. It's filling in all the sections. You can see that the graph paper, right, the grid actually is starting to take shape. To speed things along here, I have this inserted intentionally so that we can actually watch it, but if you take it out, it'll go a lot faster. Will it go too fast? Oh yeah, really fast. Ooh, yeah. You could still see the motion. Maybe somewhere in between would be better. Maybe just 100 milliseconds to slow it down. Yeah, there we go. Cool. Notice that for each of the divisions, it's going in the same order that I did it. Lower left, upper right. It's doing the exact same order. To wrap things up here, since I know we only have a few minutes left in class, let's mess around with that base case. If I come over here, this says if the size is less than 0.5, then stop. Do not do any more recursion. Do not do any more drawing. Just stop. You are done. So if I make this even smaller, it's gonna draw smaller boxes, right? That's the idea. So let's add another 0 out in front and see what happens. Oh my goodness, I think that might be a little overkill. It's still technically a grid, right? But not a very easy to use one. So you can see that, yeah, it does have an effect, but it was also going to take a heck of a lot longer too, because it had to draw more and more stuff. Whereas if we go the opposite direction, right? If I say maybe not 0.5, but like 0.1 or something, that's bigger than what used to originally be there. We can see that, okay, it's not going to draw as big grids, and it's going to get through a lot faster because it doesn't have to make as many recursive calls before it hits the base case, as we might expect. There's a lot of other fun stuff you can do with this too, such as consider changing the colors of the lines that you're drawing based on how far down you go, for example. I think that's a fun way of playing around with this exercise even more. And as I mentioned, if you like problems like this, you're going to definitely see some more examples of this both in the studio and on the upcoming homework assignment, and there's also going to be plenty of examples of these in the practice problems for the exam that is coming up after spring break. Okay, I think this is a great place to go ahead and wrap things up for the day. Hope you all have a good rest of your week. I will see you in the labs on Wednesday for studio.